At 3 o'clock on a summer afternoon, a modern house in the desert can become completely dependent on a machine. The sun has been striking the roof for hours. Heat is pouring through the windows, the driveway is radiating warmth back toward the walls, and the air conditioner is working hard just to keep the rooms feeling ordinary. Then imagine the power goes out. Within a surprisingly short time, that sealed, carefully finished house may begin to feel less like shelter and more like a parked car. Yet not far away, there may be a much older house, built from little more than earth, water, straw, and wood. It has no smart thermostat, no high-performance mechanical system, no factory-made wall panels. Its windows may look too small, its walls almost unnecessarily thick, and its exterior may seem primitive beside a newer home. But while the modern structure reacts quickly to every change outside, the old earthen house changes slowly. The heat does not disappear, it is delayed. And in a hot, dry climate, that delay can make the difference between a room becoming unbearable in the afternoon and remaining usable until the cool night air returns. Perhaps the people who built these houses did not defeat the desert heat. They simply understood that the first job of a house was to stop that heat from entering too quickly. That idea matters again today because many homeowners are paying more for electricity, more for mechanical systems, and more for houses that cannot remain comfortable for long without constant energy. Adobe construction does not offer a magical escape from air conditioning, and it would be dishonest to present it that way. But it does raise an uncomfortable question. How did families living in severe desert conditions hundreds of years ago create homes that worked with the daily temperature cycle, while so many modern houses are designed as though the local climate is a problem to be corrected afterward? To understand the answer, we first have to clear up what Adobe actually is. Adobe is not simply a brown color, a rounded decorative style, or a southwestern look added to an otherwise conventional building. It is a method of construction. Soil containing enough clay to bind together is mixed with water. Straw or another plant fiber may be added to help control cracking and hold the material together as it dries. The wet mixture is pressed into molds formed into blocks and left in the sun until the blocks become firm enough to build with. Those blocks are stacked into walls, often using a similar earthen mixture as mortar. The surface is then covered with a protective plaster or coating that must be maintained, especially where wind and rain can reach it. The important detail is not that the ingredients are humble, it is that the finished walls can be extremely heavy and extremely thick. An Adobe house is not a lightweight shell separating indoor air from outdoor air. The wall itself becomes a large physical mass that absorbs, stores, and releases heat over time. In modern discussions about energy-efficient houses, people often hear the word insulation and assume that any wall keeping a home comfortable must have a high insulating value. Adobe works differently. Its greatest strength is not necessarily stopping heat in the same way a thick layer of modern insulation does. Its strength is slowing down temperature change through thermal mass. That phrase can sound more complicated than it really is. A material with high thermal mass can absorb a great deal of heat before its own temperature changes dramatically. When sunlight strikes the outside of a thick Adobe wall, the wall begins taking in that heat. But the heat does not immediately appear on the interior surface. It moves gradually through the material. Depending on the wall, the weather, and the way the building is designed, that process may take many hours. By the time the heat has traveled deep enough to affect the inside of the house, the sun may already be lower, the outside temperature may be falling, and the occupants may be preparing to open the building to the cooler night air. A lightweight house and an Adobe house can therefore react very differently to the same afternoon sun. Think of a thin metal pan and a large stone sitting outside. The pan becomes hot almost immediately because it has little mass and responds quickly. The stone warms much more slowly. It may still be absorbing heat after the air begins to cool, and it will release that stored heat slowly afterward. A lightly built house can behave like the pan. An Adobe house behaves more like the stone. Neither one destroys heat, they simply handle time differently. And time is one of the most valuable tools available in desert design. The hottest part of the day does not last forever. If the building can delay the indoor temperature rise until the outdoor temperature begins dropping, the occupants gain several hours of comfort without asking a compressor to do all the work. That does not mean a thick earthen wall by itself guarantees a cool house. A badly designed Adobe building can still overheat. A wall exposed to intense sun from the wrong direction, a room with too much glass, or a building that cannot release stored heat at night can become uncomfortable. The wall is only one part of a larger system. Traditional desert houses often combined that thermal mass with a series of smaller decisions that reduced how much heat reached the building in the first place. Windows were commonly smaller than the dramatic glass walls seen in many new homes. That limited the amount of direct solar energy entering the room. The windows were often set deep within the thickness of the wall, which naturally shaded the glass for part of the day. Roof edges, porches, covered walkways, and projecting elements helped keep sunlight away from doors and walls. Courtyards created protected outdoor areas where the building itself could provide shade. Rooms could be grouped compactly, reducing the amount of exposed exterior wall compared with a more scattered layout. Light-colored surface finishes reflected more sunlight than dark walls and roofs. Openings were placed with wind privacy, security, and the path of the sun in mind, not simply arranged to make the exterior look balanced from the street. None of these choices sounds as impressive as a new cooling system. That may be why they are so easy to overlook. A shaded window does not advertise itself. A deep wall does not send a monthly report to your phone. A carefully positioned room simply feels less punishing at 4 in the afternoon. But for a family living through a long desert summer, that ordinary comfort would have shaped the entire day. It could determine whether a child could rest, whether an older adult could remain in the house safely, whether cooking made every room hotter, or whether people had to abandon the interior until after sunset. Good climate design is often invisible because its success feels like the absence of a problem. The most interesting part of the Adobe system begins after the sun goes down. Hot, dry desert regions often experience a meaningful drop in temperature at night. That difference between daytime and nighttime conditions gives the occupants an opportunity to reset the building. When the outside air becomes cooler than the indoor air, windows and doors can be opened. Air moves through the rooms, carrying away accumulated heat. The cooler air also passes over the heavy walls and floors, drawing heat from those surfaces. The building is not merely ventilated, its physical mass is cooled so it can absorb heat again the following day. This strategy is often called night flushing. The phrase sounds technical, but the daily routine is simple. Open the house when the night is cool. Let air pass through it, cool the walls, floors, and interior surfaces. Then close the windows and block direct sunlight in the morning before the outside temperature climbs. In a climate where the nights are sufficiently cool, the house begins the day with a reservoir of coolness stored in its mass. The walls then spend the daytime hours absorbing heat, instead of quickly allowing the interior air to follow the outdoor temperature. The house is almost charged with cool air and cool surfaces overnight. By late afternoon, that charge is gradually being used up. Then the cycle begins again. This requires the occupants to pay attention to the climate. The building cannot be treated like an isolated box that remains in the same condition all day and all night. A window that should be open at 10 in the evening may need to be closed at 8 in the morning. A shaded courtyard may be pleasant before noon and warm later in the day. The household schedule follows the movement of sun and air. Some people may see that as inconvenience. Modern heating and cooling systems allow us to ignore many outdoor changes, and that is a real benefit, especially for people with health concerns, limited mobility, unpredictable schedules, or little tolerance for heat. But there is also something revealing about a house that asks the occupants to work with the day instead of constantly overpowering it. The building performs much of the work passively, while the residents make a few well-timed adjustments. Compare that with a poorly oriented modern house containing large west-facing windows. In the late afternoon, sunlight enters directly through the glass, striking floors, furniture, and interior walls. Those surfaces absorb the energy and release it into the room. The cooling system removes the heat, but the sun continues adding more. The thermostat senses the rising temperature and calls for more cooling. The house may technically have excellent insulation, yet one uncontrolled glass area can create a problem that equipment must solve every sunny day for the life of the building. Add a dark roof, a wide unshaded driveway, limited cross-ventilation, and outdoor mechanical equipment surrounded by hot pavement, and the home begins to resemble a collection of heat problems connected to a powerful machine. This does not mean contemporary houses are badly built by definition. Modern construction can provide excellent insulation, tight air control, moisture management, filtered ventilation, high-performance windows, and reliable cooling. Those features protect people in conditions that older buildings could not handle safely or consistently. A well-designed modern desert house can outperform a traditional Adobe house while still borrowing many of its principles. The problem begins when the same general house shape is repeated in different climates with only the equipment changed. A design created for a mild or humid region may be placed in a desert subdivision with larger cooling equipment, darker paving, and little concern for the afternoon sun. Instead of starting with the local climates, the builder starts with a familiar floor plan and expects technology to correct the mismatch. Traditional houses usually had fewer opportunities to do that. When mechanical cooling did not exist, the shape, mass shade, and orientation of the building had to matter. A mistake could not be hidden behind a lower thermostat setting. That pressure encouraged a kind of practical honesty. A wall had to do something. A courtyard had to provide relief. An opening had to admit light and air without turning the room into an oven. When people describe Adobe houses romantically, it is easy to imagine a peaceful interior with softly rounded walls and beautiful wooden beams. But the real lesson is more demanding. These buildings were not comfortable because Earth is automatically comfortable. They worked when the material, climate, design, maintenance, and daily routine supported one another. Remove one of those pieces, and the performance can change quickly. Consider a hypothetical couple moving from a conventional air-conditioned home into a small Adobe house. On the first evening, they open windows and feel the cool desert air move through the rooms. The thick walls have shaded recesses around every opening. The interior feels quiet and protected. The next morning, however, they leave the windows open after the outdoor temperature rises. Hot air enters, and the walls begin the day warmer than they should. In the afternoon, they discover that thermal mass cannot rescue a house that has been filled with hot air for hours. The following day, they close the building earlier and shade the sunny openings. The interior remains more stable. The difference is not a hidden technology. It is timing. Now imagine an older homeowner who wants to remain independent but cannot tolerate dangerous indoor heat. Passive cooling features could reduce the speed at which the house heats up during a power interruption, giving that person more time and a safer margin. But passive design should not be treated as a substitute for reliable cooling, where health and climate conditions require it. A responsible modern home might use thick interior mass, exterior shading, good insulation, efficient windows, ceiling fans, night ventilation when conditions allow, and a smaller mechanical system for the periods when passive methods are not enough. That combination is less dramatic than declaring that an ancient wall has made air conditioning unnecessary. It is also more useful. Adobe's limitations become especially clear when the climate changes. Thermal mass performs best where hot days are followed by much cooler nights. The wall absorbs heat during the day and releases it when the outside air can carry that heat away. In a hot, humid climate, where nighttime temperatures remain high, the building may have no effective way to discharge what it has stored. The wall can remain warm, and the interior may never receive the cool reset it needs. Humidity also changes how people experience heat. Air movement and lower surface temperatures can help, but when the air is already carrying a great deal of moisture, natural cooling methods may not provide safe or comfortable conditions. Mechanical cooling and dehumidification remain important in many hot, humid regions. This is why copying the appearance of a desert house without understanding the climate can lead to disappointment. A thick earthen wall in New Mexico and a thick earthen wall near the Gulf Coast are not operating under the same daily cycle. One may release heat into cool night air, the other may remain warm through the night while also facing heavier rain and moisture. Adobe is local architecture in the deepest sense. Its success depends on where it stands. There is another misunderstanding worth correcting. Thermal mass and insulation are not interchangeable. A massive wall slows temperature change, but over a long enough period, heat can still move through it. During a prolonged heat wave with very warm nights, the wall may gradually become hotter each day because it never fully cools. In a cold winter, an uninsulated adobe wall can lose indoor heat despite its thickness. Modern energy codes may require additional insulation, and builders may combine earthen construction with insulated assemblies to achieve dependable year-round performance. That can create a better house, but it also complicates the romantic idea that anyone can dig soil from the yard, shape a few blocks, and build an inexpensive home. Soil composition matters. Structural engineering matters. Foundations matter. Roof loads, earthquakes, drainage, electrical work, plumbing, permits, labor, and code compliance all matter. Traditional material does not automatically mean low modern cost. In some areas, skilled adobe labor is limited. Repairs may require knowledge that a conventional contractor does not have. Insurance and financing can be more complicated. Building codes may restrict which systems are accepted or require engineered details that increase expense. A homeowner attracted to adobe because the material appears free may discover that the earth is one of the least expensive parts of the project. The most serious physical enemy of adobe is water. An earthen wall can endure for generations when it is protected, but concentrated moisture can erode it. Roof leaks, poor drainage, rising damp from the ground, wind-driven rain-damaged plaster, and water splashing repeatedly against the base of the wall can all cause deterioration. Traditional builders often relied on protective roof forms, raised foundations, maintained surface coatings, and careful repair. The familiar idea of giving an adobe building good boots and a good hat captures the principle: keep water away from the base and provide dependable protection above. Neglect can turn a small crack into a path for moisture. A failed roof edge can allow rain to carve into the wall. A modern stucco or cement coating applied without understanding how the earthen material handles moisture may trap water rather than solve the problem. Preservation records show that unprotected adobe can suffer serious damage during heavy rain and wind. That does not make adobe fragile in every sense, but it does make maintenance part of the architecture. The homeowner is not buying a wall that can be ignored indefinitely. This is one place where the human cost of a house becomes more important than its appearance. A younger owner may enjoy repairing plaster and monitoring drainage. Someone aging in place may not. A family already struggling with work, children, and expenses may not want a building envelope that depends on specialized maintenance. A design can be environmentally sensible and still be a poor match for a particular person's life. The right question is not whether adobe is good or bad. It is whether the responsibilities of the building fit the abilities, climate budget, and expectations of the people living inside it. The same question should be asked about modern houses. A large glass wall may be beautiful, but who will pay to cool the room behind it? A complicated roofline may photograph well, but who will repair the flashing 20 years later? A tightly sealed house may save energy, but who will maintain the ventilation equipment and filters? Every building asks something from its occupants. Traditional construction often asks for observation and regular care. Modern construction often asks for money, replacement parts, and continued access to energy. Neither arrangement is free. What Adobe offers is a clear demonstration that the walls, windows, roof, and layout can share the burden, rather than passing nearly all responsibility to equipment. That principle can be used even by someone who has no intention of building with earth. Start with the sun. Before choosing an exterior style or arranging rooms around a dramatic view, study which walls receive the harshest afternoon exposure. West-facing glass is especially difficult because low afternoon sun can penetrate deeply under roof overhangs. Reducing glass on that side using exterior shades, planting appropriate trees, or locating less frequently occupied spaces there can lower the amount of heat entering the home. Exterior shading is usually more effective than an interior blind because it stops sunlight before the energy passes through the glass. Deep roof overhangs can protect walls and windows when their dimensions match the sun angle. Covered porches create outdoor living space while also shielding the interior. Windows placed on more than one side of a room can support cross-ventilation when outdoor conditions are favorable. High openings can allow rising, warm air to escape. Courtyards can create shaded areas and guide air, though they must be designed carefully to avoid becoming heat traps. Light-colored roofs and walls can reduce solar absorption. Trees, trellises, and covered walkways can shade the surfaces that would otherwise store heat all afternoon. Thermal mass can be introduced through concrete or masonry floors, interior brick walls, tile, stone, or engineered earthen systems. But mass should not be added blindly. It needs to be protected from excessive solar gain and given a way to cool. A dark masonry floor directly behind a large west-facing window may absorb enormous amounts of energy and release it into the room after sunset. The same floor shaded during the day and exposed to cool night ventilation can help stabilize indoor temperatures. The material has not changed. The design around it has. Modern insulation can then be used to reduce the total amount of heat entering the building over longer periods. This is where a thoughtful hybrid often makes more sense than strict imitation. Use insulation to resist heat flow. Use thermal mass to slow temperature swings. Use exterior shade to prevent heat from arriving. Use ventilation when the outside air is beneficial. Use efficient mechanical cooling when passive strategies are no longer enough. Each part handles a different piece of the problem. The result may not eliminate the air conditioner, but it can reduce how often and how aggressively the system must operate. More importantly, the house may remain livable for longer when the equipment is unavailable. That resilience is becoming easier to appreciate as people experience grid failures, extreme weather, and rising utility costs. A home that immediately becomes dangerous when one machine stops is not necessarily advanced. It may simply be dependent. There is also a psychological difference between a house that protects you passively and one that must constantly announce its effort through fans, compressors, vents, controls, and bills. Thick walls and shaded openings can create a sense of refuge. The rooms may feel quieter. Deep window recesses make the boundary between inside and outside physically visible. The building seems substantial because it is substantial. That feeling should not be confused with proof of performance. But comfort is not only a number on a thermostat. Radiant surface temperatures, air movement, glare, noise, and the sense of being protected from harsh conditions all affect how a room feels. A person sitting beside a hot window may feel uncomfortable, even when the thermostat reports a reasonable air temperature. A shaded room with cooler wall surfaces and gentle air movement may feel better at the same temperature. Traditional desert design often addressed those conditions together because it had no choice. Modern design can do the same, but only when comfort is treated as more than supplying cooled air. None of this requires pretending that the past was easier. Traditional Adobe houses could be crowded, dark, dusty, difficult to maintain, and uncomfortable during unusual weather. People living in them did not have modern refrigeration, reliable plumbing, filtered air, advanced medical knowledge, or the freedom to select from countless building systems. Some houses were created under conditions of poverty, colonization, forced labor, limited resources, or social arrangements that should not be romanticized. The fact that a building contains intelligent climate responses does not mean every part of the life surrounding it deserves to be recreated. We can respect the knowledge built into the walls without turning hardship into a lifestyle advertisement. That distinction matters because housing conversations are often pulled toward extremes. One side treats every old method as backward, the other treats every traditional method as pure, affordable, and naturally superior. Real houses are more complicated. Adobe can provide thermal stability, local material, use, beauty, quiet, and a strong connection to place. It can also require careful detailing, skilled labor, maintenance code approval, moisture protection, and supplemental insulation or cooling. Modern construction can waste energy through careless orientation and excessive glass. It can also provide safety, accessibility, sanitation, consistent comfort, and structural performance that older buildings may lack. The useful question is not which century wins, it is which decisions still make sense. Imagine designing a modest desert home for a couple who plan to remain there into their 70s. They do not need to reproduce a historic building. They need a bedroom and bathroom without stairs. They need doors wide enough for future mobility changes. They need shaded windows that are easy to operate, not heavy shutters requiring constant lifting. They may want a courtyard, but it should be accessible and simple to maintain. They could use insulated walls containing enough interior mass to moderate temperature swings. A deep porch could protect the main living area and provide a place to sit outside in the morning. The west side could contain storage, a laundry room, or a garage buffer rather than the primary sitting room. The roof could be light-colored and designed for straightforward repair. The ventilation system could allow night cooling when outdoor air is clean and cool, while efficient mechanical cooling remains available during extreme heat, wildfire smoke illness, or nights that do not cool enough. That house would not be an Adobe museum. It would be a modern home that learned the correct lesson, make the building perform, before asking the equipment to rescue it. For a homeowner who already has a conventional house, smaller changes can still apply. Exterior shades may reduce late-day heat more effectively than replacing furniture or lowering the thermostat. A tree placed to shade a west wall can change the temperature of that surface for years, though species roots, fire risk, and water use must be considered locally. Weather stripping and insulation can reduce unwanted heat flow. Attic ventilation and roof improvements may help depending on the assembly. Opening windows at night can be useful only when outdoor temperature, humidity, air quality, noise, and security make it sensible. Closing the house early in the morning can preserve cooler indoor conditions. Ceiling fans can improve comfort without lowering the actual air temperature, allowing some people to use less mechanical cooling. None of these steps is universal advice for every building. They are examples of thinking in systems rather than searching for one miracle product. That may be the most important thing the Adobe House teaches. Comfort does not come from a single wall material. It comes from controlling when heat arrives, how much enters, where it is stored, and how it leaves. Shade prevents part of the problem. Mass delays another part. Night ventilation removes stored heat when the climate cooperates. Insulation slows long-term transfer. Occupant habits adjust the building to changing conditions. Mechanical cooling covers the periods when the passive system reaches its limit. When those parts support one another, the house becomes less demanding. When they fight one another, the utility system pays the price. As the desert sun sets, an adobe wall that absorbed heat through the afternoon begins to release it. The outside air cools. Windows open, air moves across the heavy surfaces, preparing them for another day. Nothing about the process is instant. That is exactly why it works. The house does not panic when the sun reaches its highest point. It does not attempt to hold the interior at one unchanging temperature through brute force alone. It stretches the heat across time, reduces the sharpest extremes, and waits for the night to help. Adobe does not make heat disappear. Thick walls delay its movement. Shaded openings reduce how much enters. Cool night air carries stored heat away. The building follows the rhythm of the climate instead of behaving as though the desert exists only outside the property line. We should not conclude that everyone ought to build a house from mud, abandon air conditioning, or accept discomfort in the name of tradition. The more honest conclusion is also more challenging. A sustainable house is not necessarily the one containing the most technology. It may be the one that needs technology less often, because its walls, windows, roof, and orientation were designed to do real work. The forgotten wisdom of Adobe is not that the past had a perfect answer. It is that people once began the design process by asking what the sun, wind, soil, and night air were already doing. Perhaps a truly modern house should begin with the same question. Before we ask how powerful the cooling system must be, we should ask how much of the heat the house could have kept out on its own. A good home should protect the people inside before the thermostat is touched. And the best lesson hidden in those old desert walls may be this: a house does not need to conquer the place where it stands. It needs to understand it.